Okay, in the previous video, we developed this nonlinear system of equations that I've copied down here on the right. And by the way, I had a typo in that. I forgot to add the area here at the end for this airfoil section. This is the lift produced by that airfoil section. It has some finite thickness. I forgot to add the area there. So in fact, I'll just scroll back up and put that in another color here. Right here, we should have had an S sub I, and you can see that I just forgot to copy it down here from that equation there. So anyway, so here we have our nonlinear system of equations, and it's helpful to be able to linearize this in order, well, for two different reasons. Number one, to solve a nonlinear system of equations, we have to have an initial guess. Now, you could use an initial guess of all of the gamma values are just equal to 0, and then iterate on the solution until it converges, and hopefully it would converge. But it's nice to have a better initial guess, something that we think is closer to the actual solution, and we can get that by linearizing and making some approximations for this nonlinear system here. We can make some approximations to linearize that. Another reason we might want this is actually as a solution itself. You know, if the nonlinear system takes several iterations to converge, and maybe we don't need that kind of accuracy. Maybe a linear approximation for this system of equations is accurate enough for our application, which is probably true for wings with higher, larger aspect ratios, and maybe not as much sweep or dihedral. So anyway, I haven't really looked at the limits of the linear approximation to see really where it's more accurate, but in general, it's nice to have that as either a starting point or as an estimate of the solution. Okay, so we're just going to walk through that process here. Let's see. First of all, we're going to look at this lift coefficient over here, the CLI. This lift coefficient, and in general, that can be a function of our angle of attack and deflection. If we have a flap deflection, well, we can assume that that's going to be a linear angle of attack, or a linear function of an angle of attack. So let's say that CL comma alpha, and still that can be that lift slope can be different for each section along the wing. So we're going to still subscript it with I here. This is the lift slope at that particular wing section. And it would be multiplied by the local angle of attack minus the zero lift angle of attack at that location, plus epsilon I times delta I. Epsilon I is an efficiency of the flap, and then delta I would be the flap deflection. Okay, so we're going to say that the lift is linear, with each of those. And now remember, alpha I is actually defined as, so alpha I, we defined it earlier actually as the tangent or the tangent of alpha I was equal to the local velocity VI dotted with the unit normal divided by VI dotted with a unit axial. Okay, so that's the general definition of the angle of attack, and this is actually equal to a sine of the alpha I over cosine alpha I. Right now, if we assume that our angle of attack is small, which is generally true for the cases for which we'd be using this numerical lifting line algorithm, then we can say that cosine alpha is about 1, and sine of alpha is, we're going to approximate that as alpha I, okay? And so now we can say, we can equate this alpha I to that, and so what we get out of this is that alpha I can really be written as or approximated as VI dotted with our unit normal, okay? So that's an approximation for the angle of attack. That helps get some of the nonlinearity out of this equation. So if we look at this general solution up here, this nonlinear system, part of the nonlinearity is that this v sub I depends on all of the gammas. So actually this term right here is v sub I, and it depends on all of the gammas, and we had the ratio of that in order to even get alpha I. Well, now we've linearized that, so alpha I is just vi dot uni. Okay, so let's actually just write that out here. So alpha I equals vi, which is v infinity plus the summation from j equals 1 to n of gamma j over 4 pi times vji, that's our influence. So that's our vi, and then we're going to dot that with uni. Okay, so that's our unit normal for that particular section. Okay, so that's our estimate for the angle of attack. Okay, the other place we have a nonlinearity in this system of equations is the fact that we have gamma I here multiplied by gamma j. See, this is the summation of all the gamma j's. We're going to multiply that by gamma I. So this is a nonlinear term here. So for the sake of linearizing this, we're simply going to drop the nonlinearity inside of this portion of the equation. So we're just going to neglect this summation when we compute this portion of the equation. Okay, so let's just write that. We're going to neglect the gamma I multiplied by gamma j, right? That's a multiplication, not a dot, I guess. So gamma I times gamma j. Okay, so let's now rewrite this system of equations without these nonlinearities built in. And so what we're going to get is, and actually I'm just going to move this density. Actually, see, this density is just a constant. And once we can actually just move that outside of this magnitude sign. And same with gamma I. The magnitude really applies to this vector. We have a cross product here, this vi cross li. So I'm going to move this magnitude in and move this gamma and rho outside of it. And actually there's a rho over here. And since this whole thing is equal to 0, we can cancel those rhos. So I'm just going to drop rho, and I'm going to be left with the magnitude of v infinity cross li. Remember, we dropped all of this summation term here, so we're left with v infinity cross li. And then on the outside of that, I'm going to have gamma sub I. And now we're going to plug this alpha I term into this expression here and substitute that in for this right here. So what I get, and yeah, let's just write this out. So we're going to get minus 1/2 v infinity squared, and I'm going to move that si there right after v infinity so I don't forget it this time. And then we get cl alpha I from this stuff up here. We're going to, and then multiplied by alpha I, and I'm going to plug in this alpha I here, which is v infinity plus the summation from j equals 1 to n of gamma j over 4 pi times vji dotted with uni. And then we've got minus alpha L0i, again filling in up here, minus alpha L0i plus epsilon I delta I. Okay, and so that whole thing is equal to 0. Notice I dropped the density here and there. I think I got the rest of the terms in there. Okay, so now let's split this up just a little bit more. I'm going to take this 1/2 just because I don't like carrying fractions around. I'm going to multiply everything by 2. So that will just put a 2 out in front of this term here. And so what we'll get is a 2 times v infinity cross li times gamma I. And then the second term I'm going to divide up into all of the constant values. I'm going to move those to the right-hand side of the equation. And then on the left-hand side, I'll be left with our unknowns. So our unknowns are gamma j, and our known values are like we've got alpha L0i, epsilon I delta I. And actually, we know v infinity dotted with u and I. See, this is a vector plus another vector dotted with u and I can actually divide that up. I'm going to move this v infinity dot u and I to the right-hand side, and on the left-hand side, I'm going to leave this vector dotted with u and I. Okay, so what we'll be left with on the left-hand side is minus v infinity squared. Remember that 1/2, I multiplied everything by 2. So we've got multiplied by si, and then cl alpha I. And on the left-hand side, I'm going to leave this summation of from j equals 1 to n of gamma j over 4 pi vji dotted with, and that's a vector, dotted with u and I. Okay, so that's left on the left-hand side, and then on the right-hand side, I'm going to move the rest of this stuff over, which was equal to v infinity squared si times cl alpha I times, we've got a v infinity dotted with u and I minus alpha L0 I plus epsilon I delta I. Okay, let me just make sure we got everything over there. Okay, I think we're looking good. Yeah, I think we're good. So this is our linear system of equations, and we can write this as we can write this equation for each horseshoe vortex again, and so we'll end up with a system that looks like this, where we're now solving for our vector of gammas, and so we can write the system of equations, and we're going to be solving for gammas. Notice we don't have any nonlinearities now. So we've got gamma I here, but that's not multiplied by any other gammas. We've got a summation across all of the gammas, but that's not multiplied by any other gamma as well. So this is a linear system. We can put this into this system of equation down here, invert this matrix, multiply it by the value on the right-hand side for each of our vortex segments, which is this expression here. So we can fill out the right-hand side there, invert this matrix, multiply by that, and that gives us a solution for gamma, a solution based off of this linear approximation. And again, that can be used as either now a starting point for my nonlinear solver, you know, if I'm maybe using a Newton's method to solve that, or if that's good enough approximation, I can just stop there and use it as an estimate for the solution.